giving you the rundown, we will introduce the speaker today. Then we'll hear a seminar for about 40 minutes. After that, here in the classroom, we'll discuss a few discussion prompts for 5 minutes. Those who visit on Zoom may join a breakout room or stay in the main room. Those who join the breakout room might discuss the questions, the discussion prompts there for 5 minutes. And after that, we will join all together back in the main classroom to have Q&A. And with that, my great pleasure to introduce our speaker, Mike McVay. Mike McVay earned a Bachelor of Science in Geologic Engineering and a Master of Science in Hydrology from the University of Idaho. He is registered in Idaho as a professional engineer and as a professional geologist. Mr. McVay works for the Idaho Department of Water Resources and specializes in aquifer characterization and groundwater modeling. And he will talk to us today about groundwater resources in Idaho through the lens of the Eastern Snake Plain Aquifer. Please help me welcome Mr. McVay.
You guys hear me?
Yeah, sounds good.
Thank you very much, Peter. As Peter said, my name is Mike. I am an engineer and a geologist at the Department of Idaho, or Idaho Department of Water Resources. I do characterize aquifers, and I do use aquifer modeling to help solve real-world problems. And Peter said I could give a little plug before we start, and I just want you to know, as a hydrogeologist, my job is awesome. I get to go from literally rubbing dirt in my hands to picking out pieces of rock from a well to using high-end modeling, working with professionals around the world, and sitting in courts of law and the legislature trying to explain to people what we've learned. This gives me an opportunity to do real science, varied science, and actually do something that makes a difference. To me, it was important to do more than just make money, and working for the state of Idaho gives me a path forward to helping the world at large. And so anyway, if you guys find this a little bit interesting, you can talk to me because we're always looking for talented hydrogeologists. Thank you for that, Peter. Show's over, folks. All right, the obligatory first slide, right? We all need water, and there's not a lot of it. Got to get you scared that we need to do something about our water. 3/4 of the world is covered in water, but only 2.5% is fresh water. And most of that is locked up in ice. So a very small fraction of the water we have on the planet is available to us as human beings to use for life. And it's really important, right? We need air, water, food, and shelter, probably in that order to survive. So we can see water is important. But if you think about the water resources of Idaho, that biological imperative is actually a very small part of our portfolio, excuse me. So public water supply systems and domestic wells are about 3% of our portfolio. And if you think of about those wells, they're also supplying showers and watering small lawns. So what we use to stay alive is a very small, almost insignificant fraction of our water resources. So in Idaho, when we talk about water resources, we're talking about irrigated agriculture. Almost 90% of the water we use goes to that purpose. Okay, I listed down here 70% surface water, 30% groundwater. It is very hard to distinguish these two things. Most of the aquaculture uses springs. Is that groundwater or surface water? It was groundwater a half an inch before, now it's surface water coming out. So that's one thing. I'm a groundwater hydrologist, but surface water and groundwater are intimately connected. You can almost not tell them apart. But it's more than just the water that we need to use. There's something we call the water energy nexus. And that's because we use nationwide, about 1/4 of our energy is used to moving, heating, cleaning, using water. That's a big energy load on the society, right? There's something we have to do about it. It gets even more complicated in Idaho because we actually make a lot of our power using water. So the water and energy sector, it's a growing field and it's getting more and more important as we move forward. So that's just something to keep in mind. Again, I'm looking for talented hydrogeologists to come play with me. So in Idaho, we have issues. If you look on the left here, this map is showing you a lot of our administrative areas. And so if you look at the top, I've got groundwater management areas. Those are areas where stream flows and or groundwater levels have declined. We see there's a problem. and the people that live there have to come up with a plan to mitigate for what they're doing. A critical groundwater area obviously is going to be a lot worse. These people are in trouble. This is not sustainable. If we don't do something, they will run out of water, and that's a fact. They are on the hook to develop a plan to mitigate what they're doing and do something to make it better. They've got to try to bring back their water. This is a very difficult situation. And then you can see moratorium areas. It's kind of the gray background everywhere. That's where we said no more well drilling. Some of it you can drill, but you got to come talk to me and ask me what I think is going to happen, if it's going to be okay to put that well in there. So we have issues. And you look on the right side there, you can see the map of hydrologic projects, what me and my friends do. And they're all related to those administrative basins. So if you look at the north up by Coeur Lane, we have a model of that aquifer because they have concerns about reduced flows in the Spokane River. Come down to the South Treasure Valley, we're going from agriculture to urban area very, very rapidly, and there's a lot of concern about that. We've done several studies. We have a model in this area. A little bit further to the west in Mountain Home, they have issues as well. We're building a model and doing a study right now that will link up to the Treasure Valley model. Keep going to the east, you see the East Spam there. That's what we're going to talk about today, that aquifer. That's our big daddy. It's a very old model. We've worked on it forever with people around the world. It's highly calibrated. This is one of the better models you'll ever see, but it's because we have problems. You see there's a little red area, that's Sun Valley. That's the Big Wood Valley. We have a model there for issues and concerns they have. Camas Prairie right next to it. We're doing a hydrologic study there because it contributes water to the Big Wood River. Big Lost River. There may be some crossover with INL. It's right in this area. So there's a lot of interest in the Big Lost. It's part of the East Span model, but we're making a more refined model. We actually are done calibrating it, and we're issuing the report by the end of the year. That new model will link up to the ESPA model. I just completed a multi-year study down the Raft River Basin in preparation for a model that will link up to the ESPAN model. We just started this week a study in the Portneuf there, concerns about reduced flows and reduced water levels. And then you go up to the Upper Salmon there, and we're working on improving fish flows. So there's a lot of issues going on. And if you're thinking, what was he talking about? We live in a desert. We use a ton of water. We got to expect we're going to run into issues. And that's where we're at. So as I said, groundwater and surface water are hard to distinguish sometimes, but I am a groundwater hydrologist. So we're going to talk about aquifers. At the top, you see two types of aquifers. Unconfined aquifer is probably what most of us think of. This is an aquifer below our feet. Rain and snow falls on the ground. It infiltrates and recharges that aquifer. If I drill a well in that aquifer, I'm going to have a water level at the same location as the top of the water table in that aquifer. I can see where that aquifer is. Now, confined aquifer, I've got these less permeable areas above and or maybe below. It's not allowing water to move out of this aquifer. So usually recharge of these aquifers are far away up in the mountains. The water comes in, it builds up pressure because it can't leave. And so if you were to drill a well into that aquifer, water level in the well would rise above where you intercepted that water first, and it may even flow at land surface. ESPA is an unconfined aquifer, and we're going to talk about that. And I'm just going to ignore perched aquifers because we don't care. So conventional wisdom, you've probably heard it, I've heard it my whole life, is water flows downhill. I've heard this a lot. But I'm looking at a picture here from the 1800s. Two things about that. One, they drilled a well with a wooden well rig. That's crazy. You're drilling into solid rock with wood. Love it. Number two, they have drilled that well into the earth. They're accessing water underground, and it's flowing decidedly uphill and it's discharging at the surface. Water does not flow downhill. And lastly, there's a dog in the picture, so you know it's real. So I'm talking about water levels here. It seems simple, right? I measure the water level. I told you if I look down on that well, I can find where the location of my aquifer is. But it's way more than that, right? We're not just measuring a water level. I'm measuring energy. I'm measuring elevation potential energy, and I'm measuring pressure potential energy. And we call that head in our industry. You may hear dynamic head if you're running pumps and pipes. We're just talking about energy. So not only am I measuring the water level to that aquifer, I'm measuring its energy, and I get a lot out of that simple measurement. Because water doesn't flow downhill, it flows down energy potential. It goes from high energy to low energy. Everything goes from high energy to low energy unless you're putting energy back into it. So instead of downhill, it's downhead, and we call that the hydraulic gradient. And that's the driving force to groundwater flow. So let's look at a map version. This shape right here is the outline of the Eastern Snake Plain Aquifer model. I'll call it ESPAM so I don't stumble. We're going to talk about this more later, and we'll get oriented to where we're at. But what I want you to look at is those black lines. So I've taken hundreds of wells across the plain and I've interpolated their depth of water or their head. I know what the head is, all those, and I interpolate that. It's a way of estimating data where you don't have it. And I come up with these black lines. They're called equipotential lines or groundwater contours. If you were to drill a well anywhere along those lines, your water level would be the same. The head would be the same along there. So now I'm going from high head to low head. So I just draw my lines perpendicular to those black lines because I'm flowing directly from high to low head. And that's what these red lines are. You can see in the Eastern Snake Plain, water generally flows from the northeast to the southwest. And it discharges here's Thousand Springs. I don't know if you've ever been there or seen pictures. It's pretty impressive. And then right here is the Snake River Canyon. We also have a lot of springs and reach gains. So that's cool, right? I've used my water levels and I know where groundwater is flowing because I know the energy. But I can see other things about it as well. In an aquifer, I need to know two properties. I need to know the transmissivity. That's how easy water flows to the aquifer. I need to know storage. That's how much water is in the aquifer. So I'm looking at my equipotentials. I'm looking at my energy, and I can see there's this place right here where the contours get closer. This place right here where the contours get closer. And that's because the transmissivity is lower there. It's harder for water to flow through that section. We have to elevate that gradient, get more driving force, because the water entering that portion must equal the water leaving that portion just by mass balance. And to keep the mass balance, we need more energy. And that's what you're seeing there. So now by measuring a water level, I take a little electric tape and I drop it down there and it beeps at me. And I go, hey, there's my water level. By doing that, I know where groundwater is going. I know something about the aquifer, and I can kind of see how the aquifer and the river are interacting. So if we look up here, this is called the South Fork of the Snake River. If I'm having to draw my flow lines perpendicular to my black lines, when those black lines go upstream and I draw my perpendicular, water flows away from the river. I know that this section, the river is recharging the aquifer. If I go down here by American Falls, you see I have an arrow going towards it. Those black lines are bending downstream. If I draw my 90-degree angle, it all goes back to the river. There, the aquifer is discharging to the river. They're intimately connected. And I can see that by measuring my energy. If I come down to this area and look here, you can see that those black lines and the blue line have nothing to do with each other. The water level is far enough below the river that changes in aquifer levels do not impact flow in the river. And I'll talk about this phenomenon here in a little bit, actually at length. And so things that happen in the groundwater there do not affect flow in the river. It's perched. So now I know 3 places how the aquifer is connected to the river. I know something about the aquifer itself, and I know how the groundwater is moving just by measuring water levels in wells. It's almost like magic. All right, we're moving along. I'm trying to give you some basics, then we'll get into the Eastern Snake Plain. That way, if you guys are experts, I don't have to explain as I keep going forward. So we're in an aquifer. We're talking about pumping. There's something you need to know about pumping a well. You are not sucking water out of the aquifer. You're removing water from the well bore. That's changing that hydraulic gradient. My water level is here, now it's here. Now it's flowing down gradient into my well. You're removing water from the well, and the aquifer flows toward it to fill up that space. And we can see that here. We call it a cone of depression, excuse me. And you can see that it actually is in 3D, and I've sliced it here for a cross-section view. Water table is up here, started pumping. I lowered my water level to here. Now here's my new hydraulic gradient, bringing water to my well. If I keep pumping, my water level will go down, and now my cone of depression gets larger. I access a larger volume of the aquifer to get a larger volume of water into my well, and that's how this works. So down on the right, we can see the same picture right here with the dotted lines. I started pumping this well, water level changed, I've altered the gradient, water starts flowing, but then I turn on my neighbor's well. What happens then? Well, I've got this cone trying to grab water going this way, and now they're coming at me trying to grab water too, but I've already grabbed it. What do? Well, they start a tug of war, and right in between those, because they're not getting water, the drawdown is twice as much as it would have been with just one of them pumping right in the middle. So now multiply that by thousands of wells pumping almost simultaneously across the plain, and you can imagine we can cause some pretty big drawdowns in an aquifer by doing that. So just think about that when you're thinking about, when you're driving from here to INL, there's a lot going on the sides of the roads. All right, this is getting to the crux of the problem, and I'm hoping I can walk you through it. I implied that there's sections of the river where the river gains water from the aquifer and where the aquifer gains water from the river, and it's because of this connection right here. The water is connected. It doesn't care if it's inside or outside of the aquifer. So in this top case here, you can see that my water in the aquifer is higher than the water in the river. It flows down gradient, give water to the aquifer. I'm discharging to the aquifer. I don't have it pictured here, but you can imagine if my water table was lower then that same thing applies where the gradient is going into the aquifer. And that's like it was at the South Fork, where water is now recharging the aquifer because the head difference goes that direction. Now, if I throw a well in there, I again change that hydraulic gradient. In a gaining stream, I can reverse that and make it a losing stream. In a losing stream, I can intensify that and make it a greater losing stream, losing more water to the aquifer. So pumping a well will eventually result in reduced stream flow. And that's the crux of the problem in most places in Idaho, and it's definitely the problem in the Eastern Snake Plain. Looking around, see if anybody's lost. All right, let's talk about the plain. It's our big daddy, like I said before. It is important to us socially and economically, and it's part of our water budget portfolio, water resources portfolio. So as I said, I don't know if I said this earlier. If I didn't, I'm going to say it again. I need to do two things when I'm characterizing an aquifer. I need to do a geologic framework, and I need to do a water budget. Geologic framework, as you can imagine, just imagine a mountain valley. That's going to be the bowl that's holding my aquifer, right? We're going to have all these mountains, and we can see that here. It's just bigger, so it's harder to see. So there's my bowl. We know how deep it is by doing certain tests. So now I know the size and shape of my bowl. And then I need to know what the aquifer is made of, what that bowl is filled with. So we've got solid boundaries all around. Then we have the Snake River Canyon and Thousand Springs are the last boundary of my aquifer. And this one is volcanic in origin and is filled with feet and feet, thousands of feet of basalt. It's impressive how much basalt is in this aquifer. And so just a fun fact, this aquifer formed because of the Yellowstone hotspot. Yellowstone hotspot sits in the mantle like a blowtorch. In the North American plate, it used to sit down here, down in Oregon and Nevada, and the North American plate moved, and the hotspot went up this way, and now it's sitting under Yellowstone. So what it did, it melted all that crust, the crust goes away, starts discharging or erupting lots and lots of basalt, providing a new aquifer. But it's even more interesting than that, to me at least. If you've ever driven from Twin Falls or even from Boise and gone up to Idaho Falls or up to the park, you would notice you're going up in elevation all the time. And it's what happens is that blowtorch is heating everything up. And it's just like, you might want to try this, put a marshmallow in a microwave and turn that thing on, that marshmallow just blow up. And then you shut off the microwave and it starts to shrink back down. It becomes much more dense than it was when you started. And that's what's happening here. In the Southwest, it's had millions more years to cool down. So that's settling. And up here in the Northeast, it's still really hot and it hasn't cooled down and shrunk yet. That's just kind of a fun fact. And then another fun fact, I'm a geologist, so nerdy things, but where we live in the Western Snake Plain Aquifer, it's being formed because the plate tectonics are actually pulling our valley apart like a zipper. And when that happens, the bottom drops out and then we fill it up with sediment. And so here we're on top of thousands of feet of sediment that has been slowly coming off the mountains, being eroded off as our basin falls down out from under our feet. So, okay, fun facts are over. Back to the work at hand. So this is cross section of the aquifer. Now we've got tons of wells out there, right? And every time a well driller drills a well, they have to show what they found as they went down. We can do it as professionals, so it's a lot more complete. And we go out there with engineers and geologists, and we have all our equipment. Or, you know, drillers, they may not be educated, but they know a lot about the subsurface. And these guys will pick it up and go, pink mountain rock. I don't have pink mountain rock in my vocabulary, but I know what he's talking about. You can learn a lot about these guys. And then we can take all those wells, draw a line, and make this cross section. And you can see we have several wells that have gone down to 6,000 feet, and we can't find the bottom in a lot of places. So we're talking about a lot of salt. That's part of the geologic framework. In water resources, the scientists and the engineers, we like the geologic framework. The rest of the world says, yeah, whatever, get to the water budget, man. Okay, water budget. This is kind of a confusing graph. The light blue and the dark blue are pre and post calibration of our model. But it tells you what I want you to know, and that's the recharges and discharges into this aquifer. Again, I don't want to talk about this stuff. It's kind of boring, but I do want you to see a couple of things. Number one, the biggest discharge from this aquifer is groundwater pumping to satisfy irrigated ET. ET is short for evapotranspiration, and that's the consumptive use by plants. When you sprinkle it with irrigation water or it precipitates on it, you're going to have evaporation from the leaf surfaces as well as the ground surface. And the plant is going to transpire to grow. We respire, they transpire. And so that's what we're trying to support is the growth. The biggest discharge from this aquifer is groundwater pumping. The biggest source of recharge to this aquifer is right here. It's the inefficiency of surface water irrigation. Do you see that I'm setting up a conflict here? Some people are being the biggest problem with discharge and other people are the biggest savior with recharge, right? We have issues. But remember, we're going to talk about this. This gets complicated. So that's what I want you to remember. Surface water excess recharges this aquifer, groundwater pumping discharges this aquifer, and then we have a bunch of natural stuff that's going on that we're not going to talk about. As I move forward, you can actually see it here, millions of acre feet. I'm using an acre feet, which is defined as enough water to cover 1 acre of land with 1 foot of water. It's about 326,000 gallons. Now I'm talking millions of acre feet here. We can't use gallons. We need something bigger. That's 1.5 trillion gallons and 4 million acre feet. We can't deal with trillions of gallons when we're doing math. So we use this weird unit. Hydrology is filled with just insane units. Okay, we set up the conflict. Let's talk about it. In Idaho, we are a prior appropriation state. That means the first person to get a water right has more right to that water than the next person. So if you can imagine, I come in 1884 and I give myself a water right and I'm farming, and you come in 1886 and you start farming. And it's easier to imagine in a surface water where we have canals and stuff. And I'm not getting enough water. Well, the law says I call up the water master, which works for the state, and say, I'm not getting my water. He walks over to your gate, shuts it off. You don't have any water, but I do. It's brutal, but it works. It keeps our legal system going. So now what happens with groundwater? Those people didn't come in until the 50s at the earliest. Most of these are 1960s and 70s water rights. They are always junior to the surface water users. So now I've got my 1884 surface right, and I don't have enough water. And somebody like me just told me that it's because they're pumping groundwater, it's reducing flows in the river. So I say, hey, Idaho, I'm making a water call. Shut these guys off. Now, remember, when you start pumping a well, that cone of depression starts growing gradually. And then all these other wells start pumping, and those cones of depression start growing gradually. So if I make you shut off your well so I can get water, I'm not getting my water. It takes a long time for that to happen. So we could go in and we say, every groundwater pumper, stop. We just killed 10% of our economy. Those farms all die. And the people that wanted that surface water aren't going to get that water for a couple of years. Easy. So now we've run into a problem here. Our legal framework says that, hey, I get that water. Our legal process says, give me your water. But it doesn't work in reality, because if we do that, nobody gets their water. There's a problem here. So what happens? Well, every single year, those surface water people, they band together and they say to all the groundwater people who've banded together, you need to do something. We're making a water call. And they say, we can't do that. So then they come back and say, okay, I'm going to give you a bunch of money. I'm going to get some water out of the reservoirs to give you, so that way you don't have to use your water right. We're going to do all these things, but not shut off my well. I can't survive that. Let me do something to help you. Okay, well, that's fine and good, except now every single year, IDWR comes in and estimates this is how much the groundwater people are going to owe you. So every year, the groundwater folks have no idea what they owe. And every year, the surface water people have no idea what they're going to get. They can't plan cropping patterns. They can't plan their business. It becomes very difficult. And on top of that, they're hiring millions of dollars worth of consultants and attorneys. This doesn't work. Every year we go through the same problem, and every year we're still in the same situation. So that means, okay, these groups say, enough, let's get together and do what they call settlement agreement. And so in these legal proceedings, you can go to the person and say, we want a settlement. And they'll say, okay, I agree not to sue you every year, but in lieu of that, you have to do a bunch of stuff for me every single year to try to help the problem. We understand you can't help me today, but if you do enough over time, you might be able to make me whole. So let's do that. And that's what they did. So in 2015, they got together, they got in a room, they kicked all the lawyers out, because that doesn't help anybody. And they came to agreement. Again, the groundwater people have to do all sorts of crazy stuff. We're going to talk about managed recharge and reduced pumping, because we're scientists and engineers and we just want to know what's happening to the water. I don't care about the law at this point. Okay, excuse me. I sent out questions about the modeling. I apologize. My talk was like 2.5 hours long, so I cut out modeling. But I do want to mention, because I make and use models, we typically use these models in a predictive fashion. They'll come to me and say, I want to recharge here, I want to pump here, I want to reduce pumping here, what happens? And I can give them a prediction of what will happen to stream flows. And then that way we can help optimize it, because recharge everywhere is not the same. Reducing pumping everywhere is not the same. And that's how we generally use this model. Right. Okay, so again, most people care about the water balance. We want to know about how much water there is. So all these people are doing a lot of work, doing a lot of sacrifice, trying to help this aquifer. How do we know if we're helping this aquifer? We can look at my water levels on a well. We can do certain things, but that's not very quantitative, right? The water level went up 2 feet in my well. What does that mean? It means something's better, I guess. So we need something way, and we need another way. We could try to look at stream flows. but it's plus or minus 10% uncertainty on a stream flow, and that's a good measurement. Snake River will flow 20,000 CFS. 1 CFS is 2 acre feet. 1 acre foot is 326 gallons or 326 gallons. So over the course of one day with 20,000 acre feet, that's a lot of water. And if you're plus or minus 10%, it doesn't help us. I can't use that. So let's go and look at the water balance. Okay, maybe I can use this to determine change in storage, which is the volume in the aquifer. So inflow minus outflow equals change in storage in the aquifer. That is a deceptively simple equation. Those inflows and those outflows are very difficult to come by. We spend a lot of time and money and effort trying to get at them. And it's almost unusable though, because a lot of this information comes out in the year or two following, right? I have to collect all the measurements of people's diverting to their field. I have to collect all the measurements of wells pumping. It takes a long time. You can't use that for management decisions. You can't use that to assess what we've been doing. We need a more efficient way. But you know me, I like those water levels, and they are directly to the problem, right? Because you can imagine if there's more water in my well, there's probably more water in the aquifer. And if there's less water in my well, less water in the aquifer. I'm going to leverage that situation and see if I can figure something out. How do I do it? It's pretty simple. I subtract this year's water level from last year's water level, and I have a change. And I have all these wells, hundreds of wells across the plain, so I interpolate those changes across the model area. So now I've got a volume, right? I've calculated a change in water level over the area of the model. That's a volume. But that volume includes the aquifer matrix. That's not what I'm looking for. So that means I have to go to that second aquifer property, which is storage, and see what that can do for us. You guys may have read that description. It's boring. Let's look at a cartoon. So imagine we're standing right here on top of this box, unsaturated dirt below our feet, go deeper, we're in the saturated aquifer. Now we pull a hunk of that aquifer out. This is obviously filled with rocks and water because I'm a great artist. But if we stand there and let that water drain by gravity, that's the water that's available to us. Because remember, when we're pumping a well, we're not sucking water out of the well. It is falling down an energy gradient. So we need what's available due to gravity leakage. Now that specific yield, now I can multiply that by the volume I just calculated, removes the rock from that volume. Now I have the volume of water that changed that year. This is an uncertain, it's a very high level analysis, but I can measure water levels to 1/10 of a foot. I can only measure my surface water, but plus or minus 10%. That's a lot more uncertain. That gives me some stability in this calculation, no matter how high level it is. So as you can imagine, to do this, I'm going to need a lot of wells. I need a lot of wells to do this interpolation across the plain. The fewer wells, the more uncertain it is, you're going to miss something important. So when we're calibrating the model, every once in a while we go out and we do what we call a synoptic or mass measurement. I said I was going to say something. Do a mass measurement event. And that's what we're doing there is we're going out and we're measuring as many wells in as short a period of time as we can because we're looking for a snapshot in time. And I want to compare those snapshots. And we want to do it as long as possible after the irrigation season because I'm trying to integrate everything that happened into this kind of resultant condition. And I take my snapshot and compare those over time. So what happens, you know, in last year's irrigation season, places where they surface water irrigated, the water levels are going to come up, do that leakage. Where they're groundwater irrigating, the water levels will go down during pumping. They stop farming and everything starts to equilibrate. I want that all to integrate and equilibrate into that resultant condition. I need time, but I have to stop before the next irrigation season because they start irrigating and the water levels start changing to what they're doing right now. So that's why we do it right before irrigation starts. Every single year, we measure as many wells as we can. Or, excuse me, these are every 5 years for our mass measurements. Getting ahead of myself. All right, we're going to go into it now. This is the meat of my presentation. I've shown this several times. This is the aquifer model boundary. I'm going to show a lot of pictures. And our eyes and our brains are hardwired to problem solve. Our brains like to logic things out. And so I don't want you thinking too much. I want you to look at my pretty pictures and try to understand stuff, okay? So what we're looking at, here's that Thousand Springs Reach. Here's the Snake River Canyon. Pocatello and Idaho State University is right here. Arco, Inell is right there. And Idaho Falls is kind of halfway between Pocatello and the upper edge of the model. So hopefully that'll keep you going. Now, one thing that I learned, I don't know, maybe slowly, maybe not, over the course of my career, is that as a technical person, especially working in a public resource like this, you can't just give them an answer. You and I may be able to look at it and I come and give you a number or show you a graph and you go, oh, yeah, that looks good. You know, we understand something. Normal humans don't work like that. They need context. They need perspective. They need a story. all right? And I had to learn that the hard way. And so what I'm going to hope to do today is tell you the story so you'll see that you need to have a story. Mass measurement change maps. Here's my story about my story. I'm a young hydrogeologist. I go, hey, you know, water level changes, storage, maybe I can calculate storage change this way. So I did it, 1980 to 2001. Holy crap, people were not happy. They were not happy. I take this to decision makers and they just said, you brought me a blinking red light, scaring the crap out of me, and I have no idea what to do with it. You can't do that to them, all right? They need more. Now, I forgot to tell you, we're gonna show this picture a lot, and it's always gonna be the same. The years I'm comparing are at the top. The volume that I calculated of change in storage in the aquifer is right here. You're looking at those interpolated water level changes that I was talking about. The number of wells I used for the interpolation are down here. And if you see black dots, those are the wells that I used. I've cobbled this together from several presentations, and some people don't like wells, so you'll kind of see them come and go. And then finally, this color ramp is the same for these first few pictures. So you don't have to look at the numbers. I just want you to see the relative changes in the maps. Again, I don't want you thinking, I just want you seeing and putting it together yourself. 1980, 2001, Mike, you're a bad person, we don't like you. Go back. 2002, 3.9 million acre feet. And if you're doing the math in your head, that's 1.9 million acre feet in 1 year. It's an incredible amount of water. Now I'm telling you, I showed up with a red light once, I showed up with a red light twice. They're not any happier with me, right? And I'm like, gosh, I've done such good work. Keep going, 1980, 2008, we're down 6 million acre feet. 2013, 7.5 million acre feet. 2018, we climbed out of this abyss into a really deep hole of minus 6.5 million acre feet. And remember, that was snowpocalypse, 16, 17, 18, right? That helped us. And in 2023, we're down 9.3 million acre feet. Now to go to decision makers, my decision makers are policymakers, administrators, and politicians. You have to help them understand things. My job is to help them make decisions, all right? So we got to do something different. I can't just keep doing this. But in fact, we actually measure hundreds of wells on the plain. We don't just have to go out there every 5 years. We do it all the time just as a course of normal monitoring. But it's always been, hey, this is a general monitoring, long-term stuff. Go out there when it's not muddy. Go out there when it's not snowy. Having a bad day at work, maybe that's a good day to go. It's just kind of wishy-washy. But we're asking a lot. That settlement agreement occurred in 2015, and we're asking a lot. So instead, now we have shortened it to that same time period that we did for the larger mass measurements, because we're trying to take that snapshot at the same exact time of year. And that way I can integrate it into the other data. Okay, same as before, the years are at top. The volume's right here in the kind of center. The wells are at the bottom. And again, these colors are all related to each other. You can just look at the pictures and try to understand what's going on yourself. You don't really need to know the numbers. So 15 to 16, we haven't started the settlement agreement. We lost 300,000 acre feet from the aquifer in 1 year. 16 to 17, snowpocalypse, man. I come in, hey, look, a positive number. They're still mad at me. You showed me 1.9 million acre feet lost in 1 year, and now we have more snow than I've ever seen, and it's only 800,000 acre feet? Did you do something wrong? They really weren't happy. I was really confused. So let's look at this for a second. What's going on? Well, one, you can see some of our managed recharge. There's a recharge pit here, some recharge pits here, and they've got some injection wells down here. So we can see that. I'm not going to talk about this yet. I want you to think about it. There's this red dot here that keeps showing up. And then most importantly, look through here. There's a lot of pink. And we make these measurements in March. So that's high elevation stuff. It's still frozen. That water's still entrained in ice and snow and hasn't been introduced to the aquifer yet. It doesn't know that that happened. Go to the next year, 1.6 million acre feet. Everybody's happy. Another lesson learned, things in hydrology do not follow a calendar year. Things smear out over time, and you got to realize that. My decision makers want the answer for this year, and it's just hard. It's nuanced. You got to let them know that stuff. And look what's going on. We've got a lot of running around, a lot of water. We've got water to do recharge pit. We run along the Milner-Gooding Canal. It leaks, recharge pits, injection wells. Things are looking good. We're doing a lot of help for ourselves, but Mother Nature is obviously helping us too. 2018-19, 30,000 acre feet lost. Now, this is a high level analysis, and I do not like to report to less than 100,000 acre feet just to keep myself safe. But again, I'm working for people that don't think like that. They need flavor, they need context. So I tell them negative 30,000 acre feet. But you and I and the walls, we know that's just the ugly side of zero. Let's call it good. We made it. We're equal that year. 2019 to 20, we gained 400,000 acre feet. Look at my little red area. Remember I told you that recharge is the number one, leaky canals, the number one recharge mechanism? They put it in a pipe there. There's no more recharge. If I look at the hydrograph, the water levels in that well, it goes like this. Usually water levels follow the climate, gone. There's no water left in that area. 2021, things are getting back to normal, 500,000 acre feet. You can see these areas where we're doing recharge are red. We're still doing recharge, but it's relative to the last year. So we have a lot of really good years. We built up the aquifer. I'm still recharging, but necessarily is less because Mother Nature is not helping me. So we're losing water. We're losing water from the aquifer while we're putting water in the aquifer. 1.3 million acre feet. Ouch. And we were doing stuff. 1 million acre feet, 2022 to 2023. And then last year, 800,000 acre feet. And notice my red spot's still there at the bottom. Okay, so going through time. Now, I can tell these people a story. I can put this in perspective, and I can draw this graph. So 1912 to 1980, USGS did the ins minus outs methods of calculating change in storage. 1980 until now, I've done the water level changes method. What's going on here? Well, the pioneers come out here, the settlers, they start wanting to irrigate. So what do? They need to build canals. They go out there, sticks, they have mule teams dragging logs. They've got some dynamite and pickaxes, and they're building these rudimentary canals that leak a lot. So they're pushing water out in the desert. It's leaking a lot. If you've probably seen old pictures or maybe even fields today where there's rows of crop and then rows of water, that's called flood irrigation. That's the way they used to do it. Those plants can't use all that water, so most of it flows down in the aquifer and causes recharge. So from first 50 years through the Dust Bowl area, they built up this aquifer. They built this aquifer up, and then we built an economy and a society around that. And then in the 1950s, something happened. Two things happened. Number one, they used to run water out into the plain to feed cattle all winter long, but then they built reservoirs in the 1950s, and they wanted to save that water. So they stopped putting that water out in the desert, shut off a big part of recharge. Number two, downhole pumping technology became viable for irrigation. So right at the same time, reduced recharge, increased discharge, bam, bam, and we can see the aquifer took a major hit. Weather helps us out. We start writing the weather, and that's you can see going on from now. Dry, wet, dry, wet, dry. But what's going on? There's more than that. Because if I go into an aquifer, nothing's happening, and I start pumping a well, and let's say I draw down the water level a foot, and the stream flow goes down 1 CFS, that's the new normal. If nothing else happens, that's the new normal. I've changed the conditions, they equilibrate, new normal. We stopped letting people drill wells and getting new groundwater rights in the 1980s. Something's still happening, something is still changing. Okay, what is that? Well, it's called the irrigation efficiency paradox. And in fact, we hate the word efficiency so much that we actually call it irrigation precision in our circles, because efficiency implies good things. And what we found is that's not actually the case. Number one, we built this aquifer artificially. Are we really going to get more efficient? So that's the first part. Second part is, okay, so pumping comes along. I reduce stream flows. I'm a surface water irrigator. I have less water. I am obligated to become more efficient. I have to do more with less. When I do more with less, I reduce the recharge to the aquifer, which reduces the stream flows even more, which makes I need to become more efficient. And now we're stuck in this negative cycle where we're just getting more efficient and reducing recharge to the aquifer every single day. And then the second part of that paradox is the consumption paradox. If we look at the right-hand side here, we're looking at data from the Henry's Fork of the Snake River. This comes past Rigby and all that area up there. So what happened in 2000 right here, they got a lot of money to improve efficiencies. They were doing a lot of flood irrigation there. So they wanted to try to slow that down. They have a lot of fish issues around there. So they thought, oh, we're going to help the river. We'll divert less. We'll be more efficient. Things will be good. And these graphs right here are the same data, just displayed differently. Okay, so we know when you over irrigate, that water is going to seep into the aquifer, and a lot of places it's going to return to the aquifer along a course of the river, and we call that reach gains. So you've got to imagine if we reduce diversions, we're going to reduce reach gains. Okay, we understand that. But you'd think there's going to be a time dislocation there, but at the end of the year, there should be more water in the river, right? I diverted less to use. Sure, a little bit less is coming back in, but I diverted less to use. There should be more water in the river. And that didn't happen. You can see down here, flow in the river, went down. So what's going on? Well, we have that problem because we're wrenching down recharge when we're getting more efficient there. But when we become more precise with our irrigation, we get into this area of optimal water application. If you're going along, you're just irrigating the way your dad and your granddad and your great-granddad did, you're going to have too much water in some places. You're going to have too little water in some places. When you get efficient, they come out, they laser level that field, they put in soil moisture sensors, and you're putting down exactly as much water as those plants need. These things are engineered to grow under irrigation, right? So now it's perfect, and they start actually using more water because they are healthier plants. Secondly, if you've got a lot of water laying on the ground, or you've probably seen those end guns in the summer just shoot up these big rooster tails into the air, that cools things off. Without that, it gets really hot out there, and those plants have to transpire more just to stay alive. They're trying to cool themselves off. So by getting more efficient, we shut off the recharge, and we actually use more water. It's a paradox. So now look at this again. That's my chart that I showed you earlier in the black line, and these blue bars here are spring discharge at the 1,000 springs. Now I want to show you this to show you that changes in storage within the aquifer do result in changes in flow in the river, and we can see that they're tightly correlated. But now we can look at this chart a little bit differently, right? We stop doing wells here, but boy, wet we go up a little bit, dry we go down a lot. Wet we go up a little bit, dry we go down a lot. So what happens? We get wet weather. We can't take advantage of it anymore. They don't flood the fields anymore. They don't run it down the canals and leak. It's just water going down the river. So those wet years don't help us as much because we got more efficient, which is hurting us in the first place. That's the conundrum that we have on the Eastern Snake Plain Aquifer. Now, we've been doing a lot of work out there trying to save ourselves. So the question is the stuff that we've been doing since 2016 helping us? I look at this graph right here. Here's 2016. Is that stabilized? Are we still going down? You only know if you're in equilibrium after you've been in equilibrium for a long time. It takes 10 to 20 years to know if we've been in equilibrium. Do you see it? A lot of people do. I'm not sure. I kind of look at these and I go, wow, we went up and we went down, and then we went back up. Not as high as before. We went back up and we went down, and we didn't go up. That's bad, right? Oh, but wait here. The next up is as high as the first one. That's good, right? Where are we at? We're not really sure. But we can use the model to help us understand what's going on. The people involved, this takes money. This takes political will to keep doing this stuff. We have to convince ourselves that we're actually doing a good job. So we can now break out that model. I usually use it in predictive mode, but now I'm going to go backwards with it. This blue line is that aquifer storage change that I was showing you in the previous graphs. And then here we took the model and we subtracted out everything we did. And so here, according to our model, would be where the aquifer storage is if we didn't do anything over those years. If we add in the state's recharge, the Idaho Water Resource Board controls all money for water in Idaho, and they pay for a lot of recharge. They're on the hook because of that settlement agreement to try to recharge about 350,000 acre feet on a 10-year average every year. That's a lot of water. If we add in the recharge performed by the groundwater people as part of the settlement agreement, we get up to this green line. If we include their pumping reductions and the recharge and our recharge and things that we don't really know about, I can't measure all of it, then we get up to the storage change that I calculated. So we're able to use the model in reverse to tell us if we've been doing a good job. All right, and this is the end here. I want to end with a little graphic. This is kind of putting together all those figures that I just showed you. We're going to animate the water level changes on the left. On the right, we're going to show you what I did with the model, where I have parsed out what the reason for these water level changes are. So if it's Mother Nature and a few other things, it's going to be yellow. If it's the state-sponsored recharge, it's going to be blue. If it's what the groundwater pumpers have been doing, it's in pink. My red friends down there in the bottom. Look at that, wet winter, it's all Mother Nature. State-sponsored recharge, that's our big spot right there. Pumping reductions by the groundwater people up here. Look at all that recharge the board's doing, and watch, look how it goes up this way when we recharge. It packs a very large part of the aquifer. Those aren't particles of water, it's a change in energy gradient, making water flow a little bit differently. 2020, Mother Nature's taken over for most of it. Groundwater folks, state-sponsored recharge. Now, we're starting to get into ugly times. Water levels are receding a little bit. Starting to see most of the impacts here are really starting to add up. Impacts due to managed recharge down here are really adding up. Mother Nature's always helped here, but we're starting to get a lot more blue. It's turning green. And here we go, last year's irrigation season. Look what Mother Nature was doing for us. We come to last year. And there we are. You can see after 8 years of recharge, we can see the board's recharge intermingling with natural recharge. We can see what the groundwater pumpers are trying to do. And this is how we're trying to help ourselves. And that's the end of my show.
Well, thank you. This gives us now the time to sit in here around the table in our teams. These are the 3 questions that we want to discuss. Those who are with us remotely, if you want to join the breakout room, please do so. If you are a student zooming in, please join the breakout room. I think Dr. Crowley will also be in the breakout room, and then you can talk about the questions there. And we'll see you all in 5 minutes. Yeah. All right, I think everybody's back from the breakout room, and we are now here in the main room, and we get ready to ask some questions. I will hand the mic back to our speaker, so he will repeat the questions for those who are online. Get started. Please.
So I hope that you can go over the slides, maybe that's like a big picture thing I'd like to just But you said the inefficiency of the like early, I guess like early 1900s and such is what built this aquifer, and now it's draining. Where did that original water come from that was able to fill it up, and why is that no longer? I get we're getting more efficient, that's why it's no longer playing out. Like where was that initial draw from, and why can't we kind of reharness like extra water just to like directly put in there? And also, what kind of like downstream effects does that have? Like, is our water situation impacting like Lake Eden stuff, or are we on kind of a different water basin? Okay. So the question generally is, we had a lot of water that we filled up this aquifer at the beginning. What happened to that water? Is it now gone? Why are we having so much problem? And then the second part of that question is, are we impacting other systems? Lake Mead was brought up. That is part of the Colorado River system or part of the Columbia River system here. And so we don't impact them at all. So Peter actually just asked me that same question. All of our water, the vast majority of our water comes from snow in the mountains. And so if you look over time, there is no real strong trend saying the water, less precipitation over time. It's more flashy. We have deeper, harder droughts, and we have wetter, wet periods. But in general, the climate's pretty stable. And it's not that that water's gone away. It's just the way that we're using it. So you can imagine at the beginning, there's just a few people up there around that South Fork, Henry's Fork. I kind of showed you that area at the beginning. I guess I can still show you that. So a lot of people up in this area. So they're getting water out of the mountains. They're just putting it everywhere. It's just flooding out in the fields. As soon as it starts coming, there's no irrigation season. They don't have an IDWR telling them what to do. So they're just chucking water out there and chucking water out there. So that hasn't really changed the source of water. It's just the way we use it. We now have reservoirs. They have what they call rainbow charts that help them tell when to release it. So if you're a farmer, you go to these 70s meetings, they're just livid with the dam operators, right? Store more water. We need more water. And the dam operators are going, I can't kill everybody and breach this dam. And so there's this interplay now. There's control over these sources, and we just can't throw it out there. The second part of that is because we've increased that irrigation efficiency, because we don't flood irrigate, when those wet years come along, we can't take advantage of it like we used to. We can't just throw it out into the farms. We have to keep it in our pipes and sprinkle it out the sprinklers. And so that's why we have that issue. We still have the source, we just can't use it the same way.
I actually had kind of two questions. One was I wanted you to clarify what it implied we made this aquifer as man-made.
Okay.
I've always thought of aquifers as kind of like natural features like mountains, and maybe I'm wrong with that. Maybe I missed where the creation of that came in.
Okay, the question is, I said we built this aquifer. I said it was a man-made aquifer, and the thought is that these are natural features, just like a mountain. And you're right, the aquifer is a natural feature, just like a mountain. What we built up was the water level in this aquifer. The water level was just a lot deeper. So if you look at this chart right here, we're now back, what, to the 19 teens. We're back to that same level. So the aquifer's still there. The aquifer's still the same. It's actually almost back to its natural condition. It's just that we inflated how much water was in it, and then we set our society on top of that, and now we're like, ooh, that hurts. Did you have a second part?
What's that little red dot at the bottom? I looked on a map and I couldn't see anything obvious. The one that you were talking about.
Oh, I went the wrong way.
Southward.
Yes.
Yeah, right.
This area right here. So that's Oakley. I don't know if you know the town of Oakley. Okay, that's there, and they have one of their irrigation was a ditch, and they put it in a pipe, and it's really dry down there. So they're not getting any overland flow from the mountains or anything. Very little precipitation, and so the only recharge they were really getting there was from that canal. And once they piped it, there's just no water available.
Isaac. Do you know why the Milner flows like every 5 years? Is that related to groundwater recharge at all?
Do you mean at the waterfalls?
Yeah, I guess so. Like, last spring, like the Milner Mile came in.
Mm-hmm.
And I don't know. It's like a once every 5 years or so thing. It seems like it's really sporadic, and I was just curious if you knew the reason for those discharges.
And so I apologize. What do you mean by the Milner flow? Like the Milner Gooding Canal?
Like the Snake, like a section of the Snake River goes up to like a substantially higher CFS than like I think the Murtaugh section on the Snake River is at like 16,000 to 25,000 CFS for like I don't know, a couple weeks.
Right. Okay. So the question is why do we sometimes have really high flows that we're talking about the Milner Reach? There's a few reasons for that. One, I want to explain that we actually dry up the river there at Shoshone Falls every year. They divert all the water for irrigation that's upstream of Shoshone Falls. And so it dries up. We separate the Snake River. And then those flows down below that are supported by discharge from those Thousand Springs. So that's one thing. So number two, if it's a really wet year, you'll get a ton of flow coming down that. Well, they'll actually stay dry because there was just too much water for us to use. Secondly, certain periods of time, the Idaho Power and some other folks release a lot of water from storage in the reservoirs for fish flow. They're trying to keep the fish habitat. They need to scrub it out a little bit and keep the temperature down, tear out some weeds, redo the sediment on the bottom of the river. So every year they will release for a couple of weeks a very large chunk of water.
So you're saying from 80 to 23, there's negative 9.5 million AF. What is kind of like the leading cause of that? Is it more suburbs, houses going in, and less agriculture in that area, or what's kind of going on?
So the question is why did we lose 9.5 million acre feet from 1980 to 2023? And it is all about how we use the water. It is just about that irrigation efficiency. Urbanization is a really big issue here in the Treasure Valley, Eastern Snake Plain, and a couple of places are going pretty quick. But it is generally that irrigation efficiency, the combination of pumping water when we didn't used to pump water and recharging less because we put it in pipes and we sprinkle it out of sprinklers.
Do we have questions online?
Well, we don't.
No. Other questions? Yes, here and then over there. Yeah.
I had a question that, like, over the years, like you said that the number of well locations that you were able to use to test the water level went down over time. Did that impact like the fidelity of the models you were making, or did your ability to make those models more accurate and using old data, did that help you kind of keep the standard of that model over time?
Okay. So the question is that, when you look at these comparisons, especially that 1980 on, you see fewer wells that I'm using. The phenomenon there is that wells fail, people move, we lose access. So over time, the suite of wells actually changes across the state. So wells drilled or that were in use in 1980 may not be even used anymore, or maybe some we said we can't use it anymore. And so our suite of wells in 2023 is different than our 1980. So we still have all those wells, they're just at different locations. So you see here when I use these, we measure fewer wells annually, but I'm still back up to the 400s because we're using that same network right now. And so as we're developing these models, we still have the information. We can still use that to calibrate the model. The heads are just in slightly different locations.
Let's take this question first and then the online question.
It seems like farmers every year are like matter about, the regulations that are put on their water rights. And last year it was like a big deal, and especially in Southeast Idaho, where you just explained.
Right. So the question is, a lot of consternation about irrigators, about all the rules around irrigation and what IDWR is doing. And other people may have noticed this last year. There was a lot of strife on the Eastern Snake Plain about curtailing water, and it was in all the papers. It was all over the place. And people were very, very angry because I told you the state and IDWR do not want to shut off these groundwater pumpers. We're doing everything we can to stop that because it is terrible. But they went into that settlement agreement in 2016, and last year, some of the groundwater districts, so there's a bunch of groundwater users, they all band together so they can combine their resources. And one of those districts said, we're not doing it. We're just not doing it. We're sick of it. We don't like you. We don't like IDWR. We're done. Well, that broke the agreement. So now remember, these people said, we won't sue you for water. We won't make a water call as long as you do what you're saying. As soon as they broke that agreement, it triggered the call. So that means they have to start shutting off. Now, usually we go through that process where we say, you're going to owe this much, and this is how much we can pay, you have to pay them, but that went away with the settlement agreement. So now we're stuck with one option, shutting these wells off. And so much to our dismay, we went out to try to shut these wells off. We actually went, and we went to the wells, and we put tags on them, said, hey, we're here. We can see you're pumping, get prepared. And that gave the politics, that gave all the decision makers time to get back to the table and do something before they actually shut those wells off. So they were upset because it was upsetting. They were upset at IDWR because they didn't understand what was going on. They thought the government was coming in and taking their stuff when actually it was their neighbor saying, hey, you're taking my stuff. And so this is one of those communication issues. You got to keep everybody informed. That's a good question.
Take the online question, then here and then there.
Dr. I will ask two questions. The first one is there a mechanism for the government to take back a water right that they have issued? Second, do you collaborate with Idaho Water Resource Research Institute?
Okay, the first one, does the government take water away? Is that what you're saying?
Right. Mechanism to government take back water rights that they have issued.
Right, so we don't really have a mechanism to take water rights. However, if you don't use your water for 5 years, it's up for forfeit. And so they say, hey, look, you didn't even need the water. Somebody else is begging for that water. So you will lose your water right if you don't use it enough. Now, there is a mechanism where you can put that water in what they call a water bank, and other people can rent that out and use it. And so we say, okay, people are using that water maybe at this location, but there is a mechanism to keep that forfeit from happening. And what was the second one? I apologize.
Water Resources Research Institute.
Yes, we do collaborate with them heavily. The first versions of this eastman model were made by IWERI, is what we call them. A lot of the people I used to work with at IDWR had worked there. We used to work very closely with them. Things have changed over time, and we've kind of lost that connection. They've recently tried to rehab our relationship, and so we're hoping to work with them more in the future. We need their help, actually.
This question, then Mark, and there was a third one somewhere over here.
So I imagine this is like a lot of work to go to every well and measure them. I was curious, like, who does that work, and how long would it take to collect enough data to make one of these?
Decades. So the question is, we need a lot of data. We're collecting water levels from a lot of wells. Kind of what are the logistics and who's doing it? Is that a good synopsis? Okay, well, IDWR does this. We have regional offices. We'll send people out, and everybody has their own little network. I have my own little network south of here in Grandview, Bruno. So everybody takes on their own little chunk. And when we do those master measurements, we have a person that does the logistics. Said, okay, everybody get together. Mark said, go, and we all go to a different location. So it's usually us and the USGS. Idaho Power also collects water levels, and they share those with us. And so it is a very collaborative effort, and it's very difficult. Now, technology has changed and importance has changed. So we drop what we call transducers into a well whenever we can. And those measure pressure changes. The transducer disforms because of the pressure. It tells me I can calibrate that to water levels. And then now I can throw it in and I can collect data all I want, every hour, every minute, every day. So now I don't have to go out quite as often. Now I can only go out a couple times a year, and that reduces that logistics quite a bit. Yeah, it's an effort.
So when we're looking at recharge locations, What is the process for choosing a recharge location, and are there any politics involved?
Okay, what is the process and the method of choosing recharge locations? Well, we do a few things. First off, when we started this whole thing, we came out and said, we're going to do all this recharge. You have to get the political will. You have to get everybody behind you to do that. And then they come to me and they say, Mike, where do we do recharge? Okay, that's kind of weird. So what do you do? Well, I look for areas where I have to do evaluations. Is the water level really high here? Is it going to flood people's basements? We have to kick those things out. Is there a canal that will take water out to this location? Because most of the time we use pits. We just want to run it in, make a pond and let that sink in. So we have access? Do we have the legal right to get there? Will somebody let us do that? And then I go in and I start running the model. Okay, so if you recharge right next to the river, that water is going to go back to the river fairly rapidly. If you recharge far away from the river, it's going to stay there. So then I developed a ranking process where we said, hey, if you recharge in this area, we'll only give you $1 an acre foot. If you recharge in this area, we'll give you $100 an acre foot. And that's how we incentivize people to do what they want. And there is a lot of politics involved in that. The general consensus among typical water users is we hate the government. I come showing up in your door, knocking on your door. I'm from the government. I'm here to help. Can I use your land to flood it? They're not going to say yes. You know, that's a very difficult proposition. We have to get buy-in from canal managers. We have to get people. We have to find the people that want to work with us. We have to find the locations that will legally let us do that. So it is quite the process. Pretty iterative as well. Did that help?
It does. I guess a follow-up question is going to be, in your ideal situation, you have more recharge places, locations, and where would you put them on this?
Oh, yeah. In an ideal situation, heck yeah, I want a lot more. So one of the issues is up here, we have a lot of water, but we don't have water rights for them. They can't take the water out and put it on the field. So that's the issue up here. We have good water rights down here at the Milne-Gooding Canal, and so that we can put them out there. And that's a really good storage area as well. It's a really good spot right here. Most of the places here are right along the river. So we have some issues there. So what we would like to do, if we could get, you know, it's hard to go across government property. You cannot go on the feds property without an environmental impact study, and those take years and millions of dollars. But if we got rid of all that, I would want to take it out of the river and go out here south of Mud Lake, just throw it out here in the middle of nowhere, as far away as I can from any river. And that's what we want to do. We fantasize that about a lot. The politicians come and fantasize, oh man, if we could get $1 billion, what do you think? I say get $1 billion. But yeah, very difficult. And my fantasies, I think about them a lot. I have this huge hydro wish list.
So I guess there's a lot of pumps on properties, I imagine, where people like haven't necessarily reserved water rights. Is there a way for people to enforce that? Like for the government to enforce if somebody is using a well and like creating drawdown without like registering or without getting water rights, and how much water does somebody have to pump out before like the government can notice that drawdown? Yes.
Okay. The question is there a mechanism to determine if the water rights aren't valid, if they're using water illegally? Is there a mechanism to say, hey, you've used too much or your drawdown's too big, we need you to shut off? The drawdown causing a shut off, no. Historically, we do not administer to water levels. If your neighbor is pumping his well and reducing the water level in your well, you get to drill it deeper. If pumping impacts impact the surface water, those are direct surface water impact or direct water right impacts, we do something about it. People do divert it legally. I used to joke with Linda, if you want to steal something in Idaho, steal water. It's easy. It's hard to enforce. So what happens usually is we'll come through and we'll do surveys. And we'll say, hey, you know, when I look in the map at IDWR, you're supposed to be irrigating here, but when I drove by, you're irrigating over there. What's going on? And so people will work with water agents in that. Most often that's neighbors. The neighbors call them and say, this jerk is irrigating illegally. You made me do this. You better make him do that. And that's kind of the process. We do have what we call a domestic exemption. So if you've got a well for your house, I think it's up to 8 members of the house, 30,000 gallons a day, you can irrigate up to a ½ acre of lawn. So if you've got a house with people and you've got less than a ½ acre of lawn, you don't have to get a water right. You can just drill that well and start using it. If people start noticing you're irrigating more, again, it's probably your neighbors, then we'll step in. You have to get a water right.
Okay.
question. What sort of education or training would you like to see decision makers have so that they have a better understanding of the information you give them?
What kind of education and would I like to see decision makers get to help make these decisions? Well, beyond getting a degree in hydrogeology, I think that's not valid. Just being open to it. You know, the people I work with are generally smart. There are a lot of smart people in this world, and a lot of those decision makers are smart. They're not engineers and scientists, but they're still smart. So interfacing with them, having them go and learn about what's happening and not worry about the politics. That's what usually happens. These people are responding to complaints from the public, and so they have to kind of almost ignore the information because they're having to deal with these people. So if there's a way for them to kind of interface with the engineers and the scientists, I think that would be very helpful. Maybe we could do some kind of, you know, seminar type thing for decision makers that we could help them understand. That might be something to think about, but they're busy and they don't like it sometimes.
Here.
Saying regarding the efficiency and the increasing efficiency of the irrigation systems, do you foresee like changes being made in how those are engineered to like intentionally try to contribute more to groundwater recharge? Like maybe trying to find a balance point between like efficiency of like farming and then efficiency of returning water back into the aquifer.
And so the question is we develop technology further with efficiencies is the way to create a technology that we can both improve recharge and keep irrigation efficiency. Well, a couple of things. One, eventually we're going to get to an efficiency that we can improve, right? We're going to get to the point where we control every single drop of water, and then that efficiency improvement will stop. Number two, I don't know if there's a technology for it, but what has actually happened in reality is we've just started managed recharge. We're just trying to replace it any way we can. Issue with that, we got to do water rights. We can't do it as long, and we can't do it as dispersed. Remember, it was going out all these fields all summer long everywhere, and so we have a much smaller footprint. But I think managed recharge is the key there.
Yes. This kind of goes back to my original thing. Where is that unused water going now? What basin are we in, and where's this water going?
The question is, where does the unused water go? The unused water continues on the Snake River, goes up and hits the Columbia River and flows out to the Pacific Ocean. So there are times when people in Washington and Oregon do try to put their fingers in our pie. They want to come up to us and say, you guys are using water incorrectly. We need more water in the river. Fortunately, it doesn't work that way, and we can kind of keep them at bay. But yeah, it just flows on out of the state.
Like, let's say we just got rid of a lot of these and just start fucking getting like really just like flooding these fields. What negative impacts would that have greater on?
So, excuse me, so we stop pumping and we start irrigating like we did in the past? Is that the question? So if we changed our irrigation practices, there would be some issues. I think in general, we would like that. That would increase the aquifer and then increase aquifer discharge, but that takes time. So I think that's going to be the biggest issue is the time. Who's doing this? Who's paying to have their plants not grow as efficiently? Who's going to take on that burden? I think that's the biggest problem is we can't go backwards. We'd have to dig out the pipes that used to be canals, that kind of stuff. Yeah, it's hard to go back.
Well, it looks like we have pretty much exhausted questions here. So thank you to all who contributed questions, and let's give another round of applause.